Something is hiding at the edge of the observable universe, hundreds of them, small, red, impossible. They appeared in the very first images the James Webb Space Telescope ever captured, and they have been showing up in nearly every deep image it has taken since. Scientists have published over 500 papers trying to explain what they are. They still don't agree. Jenny Green is a professor of astrophysical sciences at Princeton University. She has spent her career studying supermassive black holes and galaxy evolution, two of the most extreme subjects in all of modern astronomy. She's not someone who uses dramatic language casually. In 2024, after months of analysing these objects, she said this: "This is the first time in my career that I have studied an object where we truly do not understand why it looks the way it does." A Princeton professor of astrophysics, decades of research, and her conclusion was, "We have no idea." That is where this story begins. The objects are called little red dots. Astronomers gave them that name informally, a placeholder while they figured out what they actually were. But the name stuck because nothing more precise could be agreed upon, and that lack of agreement is not a minor scientific footnote, it is a crisis. Because what these objects are, or were, may rewrite what we think we know about how the universe itself was built. To understand why little red dots are so disruptive, you need to understand what we thought we knew before they appeared. For decades, the standard model of cosmology gave us a clear picture of the early universe. After the Big Bang, the universe began as a hot, dense, featureless soup of energy and particles. Then slowly, over hundreds of millions of years, the first atoms formed. Then the first stars. Then eventually galaxies. Massive structures took time to build. That was the rule. The universe, according to every model we had built, was supposed to be a slow constructor, a patient architect. You could not rush cosmic evolution. For 13,800,000,000 years, that model held. Then, on December 25th, 2021, Christmas Day, the James Webb Space Telescope launched from the Guiana Space Center in French Guiana, carried into orbit by an Ariane 5 rocket. It was the most expensive, most complex, most technologically ambitious scientific instrument ever built. A $10 billion machine with a primary mirror 6.5 meters wide, designed to see light that no other telescope could reach, infrared light. Light so old, so stretched by the expansion of the universe, that it had been invisible to every instrument that came before. The Hubble Space Telescope had served us well for 31 years, but the Hubble could not see into the very early universe. Not far enough, not deep enough. Webb was built to go further than any eye, human or mechanical, had ever gone. It took 6 months to reach its orbital position, 1.5 million kilometers from Earth, so far that if something went wrong, no astronaut could ever reach it to repair it. It deployed 344 single-point failure mechanisms perfectly, in sequence, across 29 days of nail-biting precision. And then, in the summer of 2022, it turned its mirrors toward the deep sky for the first time. What it found, nobody was ready for. Ivo Labbé is an astronomer at Swinburne University of Technology in Melbourne, Australia. In 2022, he was part of one of the first teams to analyse Webb's deep field images, long exposures of a single patch of sky, collecting light across days and weeks to reveal the faintest, most distant objects in the observable universe. He was looking for early galaxies, ancient structures from the universe's first billion years. This was exactly what Webb had been designed to find. What he found instead stopped him. Scattered across the image, and almost every deep field exposure Webb took, were small, compact, intensely red sources of light. Not galaxies in any shape he recognized. Not quasars fitting any known profile. Something else. Something that did not belong in the models. Something that, by every calculation he ran, should not have been there. He called them, informally, little red dots. Rohan Naidu, a postdoctoral researcher at the MIT Kavli Institute for Astrophysics and Space Research, was among the first to flag that these objects were not just unusual, they were common. Appearing in every direction Webb looked, every deep pointing, every long exposure. Every deep pointing you did with James Webb, you were finding a few, Jenny Green later recalled. Not one, not a handful, hundreds of them, scattered across the early universe like a signal no one had built a receiver for. Here is what makes little red dots so scientifically destabilizing. They appear to exist only during a very specific window of cosmic time. The universe was approximately 600 million years old when they first show up. By the time the universe reaches 1,600,000,000 years old, roughly a billion years later, they are gone, vanished, as if something switched them off. As of 2025, astronomers had identified 341 confirmed little red dots using Webb data. They are small, far smaller than the galaxies we see around them. They are compact, and they are extraordinarily bright for their size. That combination, compact bright red, is what creates the problem, because each of those three properties points to a different explanation, and those explanations contradict each other. The first hypothesis was that they were massive galaxies, ancient fully formed structures from the universe's infancy, but that conflicted directly with galaxy formation theory. Galaxies that large should not have existed that early. There had not been enough time for the universe to build them. The Big Bang was only 600 million years old at that point. The math did not work, but the mass problem runs even deeper than that. When astronomers measured the mass of the black holes potentially powering little red dots, the numbers came back wrong in a way that nobody had predicted. A typical supermassive black hole at the center of a large galaxy today, like the one sitting at the heart of the Milky Way, has grown over billions of years by consuming gas, stars, and other black holes. It has had time, cosmic time, unimaginable amounts of it. The black holes inside little red dots had not. They existed when the universe was less than 10% of its current age, and yet they were already massive enough to produce the luminosity Webb was detecting. That means they grew fast, extraordinarily fast, faster than any model of black hole growth had predicted was physically possible. Think of it this way. Imagine you are watching a construction site. The blueprints say the building will take 10 years to complete. You walk past one morning and the entire skyscraper is already finished. Fully furnished, lights on, people inside, not 10 years later, 10 months later. That is the level of impossibility astronomers were looking at. The standard model of black hole formation says that black holes grow from stellar remnants, the collapsed cores of massive stars. Those seeds start small. They grow slowly, feeding on surrounding gas over hundreds of millions of years. To reach the masses implied by little red dot luminosities, in the time available after the Big Bang, you would need growth rates that violate what we understand about how matter falls into a gravitational well. Some researchers proposed a radical alternative. What if the earliest black holes did not grow from stellar seeds at all? What if they formed by a completely different mechanism? One where an entire cloud of gas, massive enough to be a galaxy, collapsed directly into a black hole without ever forming stars first. These hypothetical objects are called direct collapse black holes. They were theoretical, proposed on paper years before Webb launched, but never observed. If they existed, they would start life far more massive than stellar remnant black holes, bypassing the slow growth phase entirely. The February 2026 paper from Harvard astrophysicist Fabio Pacucci and his colleagues ran radiation hydrodynamic simulations, computational models that track simultaneously how gas falls onto a black hole and how the radiation that black hole produces affects its surroundings. Their conclusion was that direct collapse black holes could reproduce exactly what Webb was observing: the luminosity, the compactness, the red colour, the abundance across the sky. But here is where the story fractures into competing certainties, because a separate team, publishing in September 2025 in the Astrophysical Journal, proposed something even stranger. What if little red dots are not black holes at all? Not yet. What if they are supermassive stars? The first generation of stars the universe ever produced, objects so enormous, so hot, so short-lived that they existed for only a few million years before collapsing. Stars hundreds of times more massive than anything that exists in the universe today. Stars that the universe tried once, at the very beginning, and never made again. These objects, called population 3 stars in the scientific literature, have been theorized for decades but never directly observed. They are the universe's missing first chapter, and their predicted spectral signatures, according to the September 2025 paper by Devesh Nandal and Abraham Loeb at Harvard, match what Webb is seeing in little red dots with striking precision. So here is where the scientific community stood entering 2026. 3 competing explanations for the same objects, all published in peer-reviewed journals, all supported by real data, all internally consistent, and all mutually exclusive. Option 1. infant supermassive black holes growing inside cocoons of ionized gas. Option 2, direct collapse black holes, an entirely different formation mechanism that bypasses stellar evolution entirely. Option 3, the universe's first generation of stars in the final moments before their collapse, objects so extreme they blur the line between star and black hole. The second hypothesis was that they were quasars, the ultra-bright cores of galaxies powered by actively feeding supermassive black holes. Quasars emit enormous amounts of radiation. They are some of the brightest objects in the universe. But little red dots did not behave like quasars. Quasars emit X-rays. Little red dots, almost universally, did not. Quasars show strong variability over time. Their brightness fluctuates as material falls into the black hole. Little red dots showed almost no variability at all. The signatures did not match. The gas inside little red dots spins at extraordinary speeds, roughly 900 kilometers per second. That number is not a typo. 900 kilometers per second. For context, the speed of sound on Earth is approximately 0.34 kilometers per second. The gas inside these objects is moving at speeds that are almost incomprehensible on any human scale. And the only known mechanism capable of accelerating gas to those velocities is the gravitational influence of a rapidly spinning supermassive black hole. But the black holes inside little red dots, if they are black holes, appear to be far smaller than expected, 100 times smaller than the supermassive black holes we find at the centers of large galaxies today. They should not be powerful enough to produce the brightness these objects emit. They look like a galaxy. They move like a black hole. They emit light like neither. James Webb is a $10 billion space mission, said Anneliese de Graaf, a researcher at the Max Planck Institute for Astronomy. And you hope to find things that are truly unknown. I think it has delivered. It's really given us a new puzzle, something that looks a bit like a galaxy, a bit like a black hole, and a bit like a star. A bit like a galaxy, a bit like a black hole, a bit like a star. In any other field of science, that sentence would be the starting point of a detective story. In cosmology, in 2024, it was a confession. The most powerful telescope ever built had found something it could not name. The universe, it turns out, is not required to make things simple for us. Then, in January 2026, a team of researchers at the Niels Bohr Institute's Cosmic Dawn Center at the University of Copenhagen published a paper in Nature, one of the most prestigious scientific journals on Earth. They had spent 2 years running detailed analyses of Webb observations, building models, testing hypotheses, eliminating what didn't fit, and they arrived at an answer. Little red dots are not galaxies. They are not quasars in any conventional sense. They are young black holes, newborns, infants in cosmic terms, and they are hidden inside cocoons. The little red dots are young black holes, 100 times less massive than previously believed, enshrouded in a cocoon of gas, which they are consuming in order to grow larger, said Professor Derek Watson, one of the lead researchers on the study. This process generates enormous heat, which shines through the cocoon. This radiation through the cocoon is what gives little red dots their unique red colour. Think about what that means. For the first billion years of the universe's existence, the earliest black holes were not naked, visible, emitting X-rays the way we expected. They were wrapped, hidden inside dense clouds of the very gas they were devouring, like something growing inside an egg. The cocoon absorbed their radiation, transformed it, and sent it back out as infrared light, red, compact, bright. We had been looking for black holes in the early universe and finding nothing, because we were looking for the signature of a mature black hole, hot, X-ray emitting, variable. What we should have been looking for was a cocoon. The Webb did not find what we expected to find. It found what was actually there, and it changed the question entirely. If little red dots are infant black holes growing inside cocoons, where did they go? Why do they disappear after 1 billion years? The answer to that question was not in the January 2026 paper. It came in April 2026 from an entirely different direction. A team of astronomers using Webb identified an unusual object in a cluster of galaxies 1.1 billion years after the Big Bang. They nicknamed it the Stingray, a triple galaxy system undergoing a violent interaction. And inside that system, they found something that had never been seen before, an object sitting exactly at the boundary between a little red dot and a conventional active galactic nucleus. Not fully one, not fully the other, a transition. This galaxy is strategically in between the little red dot population and compact active galactic nuclei, said researcher R.M. Merida, lead author of the study published in Astronomy and Astrophysics. It is unclear whether it is entering or exiting the LRD phase. Entering or exiting. That single phrase is the key to the disappearance. Little red dots do not die, they transform. The cocoon of gas is not permanent. As the black hole consumes it, gaps appear. X-rays begin to escape through the holes. The red colour fades. The compact brightness changes profile. And what was once a little red dot becomes something else. A conventional growing black hole shedding its shell, entering the universe as the kind of object we already knew how to see. They were there the whole time. We just couldn't recognise them in their larval form. There is a version of this story that stops here. The mystery was identified. A solution was proposed. Science moved forward. But there is another version, one that almost nobody talks about. The James Webb Space Telescope very nearly never launched. The project began in 1996. Its original estimated cost was $500 million. Its launch date was 2007. By the time it finally lifted off in 2021, it had cost $10 billion and taken 25 years to build. It had survived 17 budget crises, 3 near cancellations by the United States Congress, and a catastrophic testing failure in 2018 that required a complete reassessment of the launch schedule. The scientist who first proposed the Webb telescope in the 1990s did not live to see what it found. Riccardo Giacconi, the Nobel Prize-winning astrophysicist who helped conceive the next generation of space observatories, died in December 2018, 3 years before Webb launched. He never saw the first image, neither did Vera Rubin. Rubin was the astronomer who, in the 1970s, produced the observational evidence that the universe contains far more matter than we can see, the gravitational fingerprint of what we now call dark matter. Her work changed cosmology forever. She spent the last years of her life knowing that the James Webb Space Telescope would, when it launched, produce data that could finally illuminate the large-scale structure of the universe she had spent her career mapping. She died in December 2016, 5 years before launch. There is something that does not appear in any press release about the James Webb Space Telescope, something the official timeline of the project does not make explicit. The people who conceived this instrument, who fought for its funding, who designed its mirrors, who argued before Congress that humanity needed to see further than it had ever seen, many of them did not get to see what it found. Science operates on timescales that exceed human lifetimes. That is not a poetic observation. It is a structural feature of the enterprise. The researchers who plant the seed rarely harvest the crop. Jane Rigby is the Webb Telescope's operations project scientist at NASA's Goddard Space Flight Center. She has been working on Webb since 2010, over a decade before it launched. On July 12, 2022, when NASA released the first full-color science images from the telescope to the public, Rigby was in the room. She described the moment the first deep-field image appeared on the screen, showing thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length, as overwhelming. Not because it was beautiful, though it was, but because every galaxy in that image was a data point, every one of them a question, every one of them a potential answer to something humanity had been asking since the first human looked up at the night sky and wondered what was out there, and scattered among them, small, compact, impossibly red, were objects nobody could explain. Rigby's team spent the days after that first image in a state that scientists rarely admit to publicly: productive confusion. They knew what they were seeing was important. They did not know what they were seeing. That is the part of science that never makes the headline. The gap between discovery and understanding. The months and years between "we found something" and "we know what it is." The papers that contradict each other. The models that have to be rebuilt. The careers spent on hypotheses that turn out to be wrong. Anna de Graaf of the Max Planck Institute spent months analysing little red dot spectra, the light fingerprints that tell astronomers what an object is made of and how it is moving. Her data consistently pointed toward black hole accretion, matter falling into a gravitational well, heating up, emitting radiation. But the X-ray signature that should have accompanied that process was almost entirely absent. If little red dots are rapidly growing supermassive black holes, she asked publicly, why do they not give off X-rays like other such black holes? That single question drove hundreds of additional hours of observation time. Webb being redirected, proposals written and approved, telescopes on Earth coordinated with telescopes in space. And then, in late 2024, a team comparing new Webb data with decade-old archival data from NASA's Chandra X-ray Observatory found something buried in observations that had been sitting in a database for over 10 years. One little red dot that emitted X-rays. Just one, out of hundreds. But one was enough. The X-ray dot had been sitting in our Chandra survey data for over 10 years, said Andy Goulding of Princeton University, but we had no idea how remarkable it was before Webb came along to observe the field. The data was there, it had always been there. But without Webb, there was no context to understand what it meant. The X-ray dot was invisible in the noise of 1,000 other observations until the infrared eye of James Webb pointed at the same patch of sky and said, "Look here, that is what the telescope actually did. Not just see further, see differently, provide the context that made existing data suddenly legible." The one X-ray emitting little red dot appears to be in transition. The cocoon of gas surrounding its central black hole is thinning. Holes are opening in the cloud. X-rays are beginning to escape. The first light from the core punching through the shell that had kept it hidden. The researchers propose that this object represents the moment of emergence. The instant a little red dot stops being a little red dot and becomes something we already knew how to see. A birth witnessed in reverse, a star shedding not its youth, but its obscurity. Amy Lowe, the lead systems engineer for the Webb telescope's deployment, described the 29 days after launch as controlled terror. Not her words on a press release, her words in a private conversation that later became public. Controlled terror. And then, on January 24th, 2022, the final mirror segment locked into position. The sun shield was deployed. The instruments were cooling toward their operational temperatures of negative 233 degrees Celsius, colder than the surface of Pluto. The telescope worked. All 344 mechanisms, all of them, on the first try. We have no word in any human language for what it means to watch something become visible for the first time. Knowing that it was always there, that the light from its existence has been travelling toward us for 13 billion years, and that the only reason we can see it now is because we spent 25 years and $10 billion building the instrument to receive it. Maybe there should be a word for that. Here is what we know today. In the first billion years of the universe's existence, the earliest black holes were not born exposed. They were born hidden. Wrapped in the raw material of creation, gas clouds left over from the Big Bang itself, consuming, growing, transforming. Invisible to every instrument we had built before Webb. Not because they weren't there. Because we hadn't built the eyes to see them yet. 341 of them have been confirmed. There are almost certainly thousands more, waiting in Webb data that has not yet been fully analysed. Each one a record of a moment in cosmic history so early that the light carrying that record has been travelling for over 13 billion years to reach us. And what happened to them? They grew. They shed their cocoons. They became the supermassive black holes that now sit at the centres of virtually every large galaxy in the observable universe, including ours. The 4 million solar mass giant at the centre of the Milky Way, Sagittarius A, may itself be the descendant of a little red dot, an ancient infant black hole that spent its first billion years hidden inside a cocoon of gas, invisible to any eye in the universe. The little red dots are not a mystery the universe forgot to explain. They are a chapter it had kept sealed, waiting for us to build an instrument powerful enough to read it. And the fact that we built that instrument, launched it on Christmas morning, deployed it perfectly across 29 terrifying days, and then had the scientific integrity to say we don't understand what we're seeing, before spending years figuring it out, that is not a failure of science. That is science working exactly as it is supposed to. The universe is not broken. Our understanding of it was just incomplete. And somewhere, right now in Webb data that no one has analysed yet, there is another object that doesn't fit, another anomaly that will force us to rebuild something we thought was certain. We should hope for that. Because every time the universe refuses to behave the way we expect, it is telling us something true. Thanks for watching. I'll see you in the next one.